All right, take your seats. We are reconvening. So the next pre-last speaker of today is Moshe Rozali from UBC, and he's going to talk about fine-grained chaos and AdS2 gravity.
Can everybody hear me? I can't really tell if this thing is on. Am I speaking too loudly, or is that okay? Okay, no response, so it's okay. Good. So thanks to the organizer for inviting me here. It's a beautiful place. It's my first visit here. Apologies to those of you who heard some version of this talk. So this is based on work with Felix Hall, who is a postdoc at UBC. Some of it is published work. Is there? Oh, there is a little dot here. Published work here. Some of it is work that will appear probably this week. And I'm probably not going to talk about that very much, so please ask me questions about that. So this is only a 30-minute talk, so it's going to be a little bit compressed, but hopefully I'll get the main ideas across. So I'm going to start with the introduction and motivation. A previous version of this talk had that take the whole time. So I went the other way, and I gave a very short introduction, motivation, and a summary of the results. Those of you who are jet-lagged like I am can just listen to that. And then I'm going to review a little bit of the machinery needed to understand the talk. A very brief review of out-of-time order correlators and how they encode scrambling. The purpose of the work was to generalize that to probe timescales that are longer than the timescale of scrambling. So this will focus on the aspects of the 4-point function, the out-of-time order 4-point function, which we generalize. The calculational tool that we use to both define and calculate those generalizations will be in the context of AdS2 gravity. There is a relation, of course, to the SYK model, but there's not enough time to discuss that, so I'm just going to talk about the gravitational side of the duality. It's AdS2 gravity and the Schwarzian theory. I'm going to derive the Schwarzian theory quickly and discuss the aspects of it that we need. In some sense, this is the simplest possible theory of quantum gravity that is coupled to matter. And we're going to do calculation. That's the theory. Once I have this machinery, I'm going to discuss those generalized out-of-time order correlators. There's a very nice way, once you understand the ingredient of the calculation, to motivate why those are the interesting and simple thing to look at. So this will be this section number 4, this classification of out-of-time order correlators. We'll see there's 2 ways of classifying them. There's classification according to the operator ordering that appears in the correlation function, and there is an independent classification according to the time ordering of those operators that appear in the correlation function, and somehow we have to choose specific way of getting both of those. We have to make specific choices for those 2 classification, and then we get something which I'll argue is in some sense a fine-grained chaos, in the sense that it probes more detailed, increasingly more detailed aspects of the physics, and correspondingly has more and more longer and longer timescales to evolve. I'm going to conclude with future direction, and after the conclusion, I'm going to talk a little bit about the work that appears. If I have time, I probably won't have time, which is why I have the conclusion before the last part. But maybe I'll just flash it after the conclusion. Okay, so this is one transparency of motivation. Again, I learned my lesson here. So basically, the idea is to focus on the different possible timescales that appear in quantum chaos. So the motivation comes from classical chaos, where chaos is a little bit more well understood. And you should have this picture in mind. There is two things that normally are called classical chaos. One of them is the so-called butterfly effect, things that are starred nearby, very similar to each other, exponentially diverge from each other. So this is a very early time manifestation of chaos. And then there's the other manifestation of chaos, which is usually called ergodicity, which is basically trajectories become dense in the phase space. If you have a phase space of finite volume, any trajectory, typically in this chaotic system, will, at late enough time, kind of cover the whole phase space. Those two things refer to two different aspects of the physics. You can cook up some example where you have one or not the other, and also they have different manifestation. So in particular, ergodicity in classical physics is well understood to relate to the physics of transport. This is some very explicit formula. So the idea is to generalize that to quantum chaos. So in quantum chaos, the short-time manifestation, the quantum Lyapunov exponent, is very similar to what happens in classical physics, but it's quantified in terms of this out-of-time order correlator, and specifically the 4-point function. So the out-of-time order 4-point function quantifies Fourier scrambling, namely how a perturbation in the system sort of covers the whole system. This is the first thing that happens. In a single particle quantum mechanics, in the semi-classical limit, this is kind of the same thing as the divergent trajectories. Okay? This was the motivation to define those particular objects, because in well-understood context, this is the same thing as Lyapunov exponent. Long time is a completely different story. So the idea of going to longer time, two things that are important there. First of all, the traditional way of thinking about long-time physics in quantum mechanics is very different, and it's not clear what the relation is. People talk about spectral statistics or more complicated statistical probe. It's not clear precisely what the relation is. The other motivation is that unlike the early time chaos that in single particle quantum mechanics in the semi-classical limit is the same as classical chaos, the late time chaos, where you go to later and later time, quantum mechanics and classical mechanics diverge from each other. One way of saying that, which I think is usually attributed to Michael Berry, is that the limit of h bar goes to 0 and the late time limit don't commute. So basically, if you are looking at aspects of late time chaos, quantum mechanics and classical mechanics become very different from each other. And in particular, you can have new effects here, especially in the context that's going to underlie everything here, which is the many-body context. So this is the main motivation for the results that I'll discuss here. A couple of other things is classical and quantum ergodicity are supposed to be the foundation of statistical mechanics. This is why they're interesting subject. Roughly speaking, those are words that you probably heard before. If you look at the system and you only study it using very simple probes, it doesn't know what exact state you're in. Everything looks pretty much thermal. So this is very successful to explain equilibrium thermal physics. It's a little bit more tricky to discuss thermalization, the approach towards equilibrium, and all the different time scales that are associated with it. And this is not just a matter of formalizing something whose physics you actually know. We know that that's not the case because there are some many-body interacting systems that do not thermalize, and it's not completely well understood. So those are the famous many-body localized states. So it's not clear what is the precise criteria, which system do or do not thermalize. There's interesting physics to do with the transition between things that do or do not thermalize, et cetera, et cetera. So this is an interesting, it's not a mathematics problem, it's an interesting physics problem. Okay, so this was one slide of motivation. With that motivation, let me just quote the results. Okay, so The kind of complementary motivation for this is that once you kind of started thinking about out-of-time order correlators in the context of the 4-point function, you can think about higher point functions. The number of different time ordering and the number of different operator orderings will increase, and the question is, what is the meaning of all those things, and what are they good for, and what do they tell you about the physics? So this is another context in which we define these fine-grained out-of-time order correlators. They probe the dynamics beyond just scrambling. So basically, roughly speaking, you have higher and higher point functions. You choose very specific ones that have certain properties. And those things will evolve on longer and longer time scale because they probe more and more detailed aspects of the situation. That is roughly the result here. There's a couple of papers that I want to, there's not that many papers, actually, those are main papers. There's a paper by Roberts and Yoshida and some follow-ups about unitary designs. And there is a similar paper by this group here. Good. So in some sense, this is generalization of that to Hamiltonian many-body system, because those were in a slightly different and maybe slightly less physical context. Okay. When did I start? 5 past, okay, good. Okay, I don't need to do this. Good. So let me do a very quick review of the 4-point function and the out-of-time order correlators. Of course, this is very well known, and I don't have enough time to actually do justice to this, but I will just highlight the type of thing that will be important for the generalization. So as I already said, there's a kind of interesting intellectual history for that object. It's kind of started out maybe in the late 60s by some expression, some quantum mechanical expression whose semi-classical limit in single body system encodes for you the Lyapunov exponent, the classical Lyapunov exponent. But then, you know, once you have that, you can go beyond that regime. You can talk about many-body system. You don't have to be semi-classical anymore. This is something that generalizes that limit. Another kind of interesting trajectory that kind of led to that is this idea of Lie-Robinson bound and this idea of growth of operators. You start with operators that are relatively simple, and very quickly, under unitary time evolution, they become very complicated. Okay? So, so this is also something that's related to that, and the other one is Loschmidt echo, basically the idea that you can compare two nearby situations. Well, I'm not going to go into that too much, but this is another thing that is very similar to this idea of out-of-time correlator. The idea is basically look at commutator of general Hermitian operators. Okay, so you have two operators V and W, and you can think about aspect of this operator, the commutator of them, as basically what is the response as measured by W to the perturbation V. Of course, in my slide, I ordered that differently, but you have one perturbation that changes the state of the system and another perturbation measure the effect of that change subsequently. So this is an operator. You can think about measuring the how large this operator in different ways. If you measure the expectation value of this operator, this is what's related with linear response. If you measure now this famous square of the commutator, it measures kind of the sum over all squares of its matrix elements. Okay, and the expectation value is going to be evaluated in the thermal state with inverse temperature beta. So this is something that will be related to the Lyapunov exponent. There is just one more step that simplifies the problem. This commutator square, when you expand it, is a 4-point function. It's a sum over 4 different 4-point functions. And 2 of those 4-point functions are kind of simple. They're well understood. If the time separation become large, They're kind of determined by factorization. They're not very interesting, so you traditionally forget about those parts of the commutator squared, and you talk about this f of t, which is the part in which VW alternate. Okay? And that part in large n system start out small, of order 1 over n. This is the connected part of the 4-point function. So it's something that naturally starts as 1 over n, but then it grows exponentially. At some time, of course, this exponential growth has to be cut off because perturbation theory breaks down. What happens is this thing saturates. You can see that for suitable operators, this thing will be bounded, and therefore it has to be saturated. But because it started out small, perturbation theory is going to be okay for a while. This defined for you 2 time scales. It defined for you the time scale, which is related to this inverse of this lambda, which is the growth rate of that correlator. It's also defined another time scale, which is how much time does this correlator grow until it saturates. Okay? And this is the so-called scrambling time. So this is roughly log n over lambda. Good. So things that I'll need in order to understand the generalization is there's 2 aspects of this correlation function that are logically independent, but they're usually written this way. So first of all, there are 2 switchbacks of the operators. You have VW, VW, rather than VV, WW. So the operator ordering is switched back and forth. The time ordering also does the same thing. It didn't have to. This correlation function is defined for any 4 time and any time ordering of those 4 times. But the thing that expresses for you this growth is the thing in which both the operator ordering and the time ordering goes back and forth. The rest of it I already said. So as I said, what we'll do now is generalize this thing to more fine-grained operators. They're going to start out smaller than this, and they're going to therefore have a longer time to grow. Okay? As is well known and very interesting in any large N system, this is bounded. Okay, so let me very quickly, since I already know that I'll run out of time, talk about how to calculate this thing in AdS2 altogether. So AdS2 gravity is the simplest possible quantum gravity there is. Very much like AdS3, the gravitational theory is locally trivial. Any solution to Einstein theory with a negative cosmological constant is AdS3, and therefore the only thing that changes between different solutions is how the boundary behaves. What happened in AdS2 is even more drastic. AdS2 itself is over-constrained. You need to add matter fields for getting any dynamics at all. If you add a dilaton field, then you get a similar situation to AdS3, in which basically the dynamics is global. So in the end, the dynamics in AdS2 is expressed in terms of this famous Schwarzian action. So this is T of this coordinate U is some boundary degree of freedom. It lives on the boundary. It's a reparameterization mode, if you want, of that boundary of AdS2. And this is it. 1 degree of freedom in 1 dimension summarizes for you all the fluctuation of quantum gravity. That's because, of course, it's such a low-dimensional theory. And what we're going to do is we're going to do perturbative quantum gravity calculation using this action. Okay? So in order to do that, we just do a saddle point approximation. So we look at the solution, and then we expand in fluctuation around that solution. So there are different solutions that are interesting here. Since we'll be interested in finite temperature physics, then we want to talk about a black hole. We're going to keep things, at least at first, Euclidean. So this is this T of U, which is the tangent of tau of u is a Euclidean black hole in this simple theory. Okay. The periodicity is the thermal periodicity, and we chose the inverse temperature to be 2 pi. This is just a choice of units. And now we expand around the saddle. Kappa is the gravitational coupling constant. And we take back reaction perturbatively. So in particular, you have this fluctuation mode epsilon. You can look at the quadratic action. You can find out what the propagator is. So we're just doing Fineman diagram, and this is the propagator of this soft mode. So this is what I will later will denote like this. This is the sort of the basic propagator here. Now, the things that we're going to do is we talk a little bit about the generalization in terms of operator ordering and time ordering, and see the propagator here. And this is the type of simplification that occurs here in this context a lot. The propagator here is two parts. One part that cares about this ordering, one part that doesn't care about this ordering. So you could see you can simplify this calculation a lot. Okay, so now in order to do this calculation, I'll just skip everything brutally, and I'm just going to say you can couple this gravity to matter as well and do the same sort of perturbative calculation. So in order to do that, in order to do our calculation, we'll need two other vertices. We'll calculate 4, 6, 8, 2K point functions. So we always talk about by local fields, there are also going to be even number of operators like VV, WW. So we'll only need the case where the matter fields come in pairs, and then they can interact with 1 or 2 or 3 soft mode, which are sort of roughly gravitons. Okay? So this is kind of the perturbation theory. There's no time to talk about details of this. Okay, so just for the record, the 4-point function that diagnoses the scrambling is just summarized in this language with this diagram, and this is the calculation we're trying to generalize. Good. So as I said, there's going to be a particular choice of operator ordering and time ordering that's going to make everything go very simply. So now we have a higher point function, not just 4-point function. Let's think about, for example, the 6 or 8-point function here. So there is the exchange operation here. You can see very clearly in this perturbation theory, whose detail I didn't explain very carefully, that kind of every time you exchange operators, you have some opportunity to get some exponential growth in time. So therefore, you want to maximize the number of times that you exchange operators. Now, if you have 2 pairs of operators, you can exchange them just once. That's it. Okay? Now, if you have more operators, then you can exchange them. So for example, you can start with this kind of canonical ordering of V1, V1, V2, V2, V3, V3, and then you can start exchanging them. You can exchange V1 and V2, but then you can also exchange V2 and V3. So the rule is that and it's very clear, kind of it comes from the mechanics of the calculation. It's very clear that in order to get something that's exponentially growing in time, you want to find what we call the maximally braided correlator, in which you just do the maximal number of exchanges. You basically, if you have, which we call the maximally braided operator, which is V1, and then everything else commutators, the minus part of the commutator here corresponds to subtracting off something that is less than maximally braided. Okay, so in the Schwarzian theory, the nice thing here is that they're very simple set of diagrams that contributes to leading order and n. This is diagrams that generalize this diagram here. Okay, so as I said, you have to do 2 things. So we choose this maximal braiding. So this has to do with the operator ordering. I didn't say anything about the time ordering yet. Now the general time ordering will have basically k times. It will depend only on k minus 1 by time translation invariance. And those could be arranged in various ways, and there was a nice paper by Felix and collaborators that classified the previous time ordering. Roughly speaking, the classification is how many times you have to switch back, how many times you have to go back and forth. Okay? So you can classify all this Lorentzian time ordering by what's called the OTO number. You have to worry about when the switchback is necessary or not, whereas the switchback that you do in the time ordering is actually necessary. So in some sense, you want to find the number of irreducible switchbacks. So we chose our correlator to be both maximally braided or also have the maximal number of irreducible switchbacks. So this is the maximal OTO number. These two choices generalize what happened in the 4-point function to the 2k-point function, and as a result of the calculation in the Schwarzian theory of this. So this could be a function of k-1 time differences. For these particular choices, this becomes a function of only one time difference, basically the latest time minus the earliest time. Okay? And also because it's the connected correlator that has 2k operators, it becomes increasingly smaller as a function of k. So this is the result in the Schwarzian theory. I won't have time to talk about that, of course, but this is also very similar to what we find in higher dimensions. Okay, so this is what I call fine-grained chaos. So I have 2 minutes, so I'll just describe why I call it fine-grained chaos. So in some sense, you could see that two things happen here. This lambda L is the same lambda L that appears in the 4-point function. So in some sense, the Lyapunov exponent appear in all those different in all these different correlation functions. So the rate of growth doesn't change. But of course, it's kind of it's apples and oranges. It's very difficult to compare different correlation functions. The meaningful comparison here is you can compare, for example, the 8-point function to product of two 4-point functions. And you can see that what happens is that when you do this comparison, as you go up in k, this correlation function grow at a lower rate. And correspondingly, you can see that already from this formula, they grow until they saturate, they grow for a much longer time. Okay? So this is what I advertised at the beginning. You have a series of fine-grained operator in the sense that they're higher and higher 4-point function. You choose very, very specific ones that summarize this growth, and you find that they grow for longer time, and in that sense, they quantify this fine-grained chaos, conclusions just in time. Something that would be nice to understand is this relation to unitary design and frame potentials, other fine-grained probe of the system, like Renyi entropy, and I'll let you read the rest of it. The calculation in a higher dimension, at least for two-dimensional conformal field theory, will appear any day now.
All right, thank you, Moshe, for the very nice talk. All right, thank you, Moshe, for the very nice talk. Questions? Julian?
I just have one technical question and one conceptual one. Technical one is, why did you insist on this Euclidean switchback thing? I mean, if I assign a Lorentzian time to each operator.
Doing the calculation in the new paper, we're doing the calculation in the Schwinger-Keldysh way, and there the ordering on the Schwinger-Keldysh contour determine both. Yes.
So the Lorentzian ordering uniquely determines the correlator.
Sure, when you calculate that way. The way we calculate it is by doing analytic continuation from Euclidean space, and I think that's probably why we have to do both choices. In Lorentzian space, we only make one choice.
And the conceptual question, maybe it's just an invitation to say a little bit more about this fine-grained measure of complexity. Of chaos. I mean, are there situations that you know of where, say, some higher order OTOs don't saturate, whereas the earlier ones do, or something like this?
Yeah, so I mean, it's kind of hard to compare with apples and oranges, but the time in which the 4-point function takes to saturate, the time in which it's already saturated, the sigma function will keep on evolving. You can see that from the problem.
There was another question up there a second ago. No, not anymore. Oh.
Hi, I have a point of confusion on how you were getting the higher point functions from this Schwarzian effective field theory. I have this idea in my head that effective field theory should give you low point functions, and as you add higher and higher point functions, those should be irrelevant operators.
Yeah, so it has to do with this choice of particular ones. So a generic 6-point function, for example, will need 3-point function vertex of this graviton, and those don't. So there's some miracle. So the Schwarzian theory is just a particular approximation to the low energy theory of some UV completion of AdS2 gravity, and you don't know, those other vertices are ambiguous. These correlators are the only ones that are unambiguous. So there is some miracle.
Any more questions? If not, let's thank Moshe again.